I thought we already did. We already did these questions.
Okay.
Yeah, so
Oh,
we're up to a new.
more.
Yeah, we're up to the next level. All right. So the transport layer. This is where you break the packet. The data from above is now broken up into segments, labeled with ports, and this handles windowing and buffering, about which more details are coming. The two primary protocols here are TCP and UDP. There are a bunch of other protocols at layer 4 that are used much less commonly, unpleasantly, like GRE and IPv6 tunnels. If you do anything like that, you can't run them through home routers because home customer premises equipment, they call it CPE, provided by your ISP, is designed to be as cheap as possible and to serve normal users. So there's a bunch of kinds of traffic that will not pass through your home router, which is very annoying as you get more advanced in networking and you try to do fancy things such as GRE, General Router Encapsulation, can only be used by ISPs but not by home users just because of the limits of the customer premises equipment. But that's why most CPEs have an option to put you in the DMZ, where you are directly connected to the internet without passing through the home router, and then you can get all this kind of data to one machine at your house. But anyway, most people are using TCP and UDP. TCP is by far the most common because it makes sure that every bit that's sent really gets there. And how often do you want to send data and you don't really want to make sure it all got there? That's rare. So almost everything on the internet is TCP over IP. However, in the rare cases where you really don't care whether the data gets there accurately, you use UDP, which is faster. And that's where you might do something like a security camera that is just sending a constant stream of data and you really don't care whether somebody's watching or not. And if they quit watching, you just keep sending it, and if they turn to watching, you send it. That's when you do something like UDP. The TCP has a window size which has been responsible for a lot of entertaining hacks. TCP is designed to transmit data as efficiently as possible down an unreliable system. Now, when they call it unreliable, they don't mean that it fails a lot of the time, like 10%. The real failure rate is less than 1% in practice, but they mean it is going to fail sometimes. And you want to be sure that you resend everything that's missed so you know it really got there. So what you do in TCP is you start with some default window size, typically something like 8,000 bytes. Then you send some segments until that many bytes of data have gotten there, and then you acknowledge them. And if for some period of time all the data gets through without error, then you decide I could get away with a bigger window size and send more segments before acknowledging them. You can have a lot of segments sent and then one acknowledged for all of them, like this. And if you do that, it's faster because the time it takes to wait for the acknowledgement depends on the entire distance between here and there. And going to other continents is like 200 milliseconds. So if you send a segment of 1,500 bytes and then you're waiting for an acknowledgement, you're going to wait like 200 milliseconds for that acknowledgement because of the speed of light and the length of the wires, and that's wasting a lot of time. It'd be a lot better to send a bunch of segments and get an acknowledgement. This will be much faster. But if the chance of error is such that frequently one of these fails, you're going to have to send all 4 of them again. And so that is inefficiency. So there is an optimum window size, and TCP has an algorithm to scale for it. After a certain number of transmissions work, it increases it. When one fails, it decreases it, so it will automatically adjust to network conditions. So if you're downloading a file, and then the network gets noisier, it'll change the TCP. When it gets less noisy, it'll change it again to try to track this. And there's a lot of learned treatises on how well this works in situations in which it doesn't work very well and you transmit data inefficiently. The most extreme example being Microsoft Windows operating systems before Vista were incredibly bad at this. They would choose the window size so badly that if you had a 100 megabit per second network, you would actually only move 10 megabits per second of real data because it had an algorithm that very poorly chose the window size. They improved that in Vista, and suddenly Microsoft operating systems actually move at 95% of the line speed because they finally fixed that problem. So I did this morning in a coffee house on a wireless network. I was downloading Linux. So I go to Ubuntu and just try downloading an Ubuntu distribution. And so you see at first it's sending me 2 packets and then an acknowledgement, 2 packets and then an acknowledgement. Then it figures out we might as well send 4 an acknowledgement. Then after a while it sends, there's a window update. It'll send a act just here to tell you I'm going to change the window size. So here the window size was 129,000. Now it changed it to 131,000. Then a minute or two later, it's expanded all the way up to 250,000, and now you see it's like 6 frames and then an acknowledgement. So you can see this happen. The window size will adjust to match the quality of your network to try to maximize the throughput. All right, ICMP is another layer 4 protocol used for ping and traceroute, and its point is to send network control messages, things like when a router drops a packet because there's no entry in the routing table, it sends an ICMP message back to the sender saying, dude, I threw your packet away. You might want to do something about that. And it typically sends a little bit of the packet back, like maybe 100 bytes of the packet in the data part of this field, so you can tell which packet was thrown away. So then there's session layer. This is where you create a session, maintain it, and then tear it down. Something like, for example, logging in. So it knows that your data should be treated differently because you've now logged in. And then it has some rules like you timed out, so now you're logged out. That's an example here. And that is not an issue that's addressed anywhere in the network addresses, but it's addressed up at the session layer. There's going to have to be a token of some kind, like a cookie or something, so it can tell that you're logged in, and some kind of rules determining when you're logged out. So this applies to file sharing and voice and video and many other things. The presentation layer does data formatting and encryption in the case where the actual raw data is in some different format than the way the user sees it, which is typically, the simple cases are things like ASCII. The user wants to see readable text, but what goes out over the wire is numerical representations of each character. The same thing's true of JPEG and GIF. They're compressed, but when the user sees it, it has to be in bitmap format so it can map to the raster of the video card and be visible. And so, and if you have encryption, this is where it has to encrypt data on the way out and decrypt the answer on the way in, to turn it into stuff that the user can understand up here at the application layer, where it has to be normal human readable, whatever it is. That's the point of the application layer, to get things all the way up here in a human readable form. All right, so a few eye clickers about that. All right, where are switches? All right, guess I can quit at 20 on this one. All right, that's layer 2. There we are, good. Not unanimous, so I'm thinking maybe this review is worth doing. All right, so which layer delivers packets across the internet? I'll quit at 25. All right, that's layer 3, the internet layer. I'm seeing layer 4 here. That's disturbing. Okay, layer 3, the IP address is used by routers to move large physical distances. It doesn't look at anything higher at all. It doesn't care whether it's TCP or UDP or ICMP. All the internet routers care about is the IP address at layer 3. Just like physical mail, transfer stations just look at the zip code and they don't care about anything else. They just want to get it to the right region, and then the details will be handled by the local objects at that end. So layer 3 is the only one that actually moves any physical large distance. All right, which layer encrypts data? I'll quit at 25. All right, it's actually layer 6. The right answer is the last one here. Layer 6 is the presentation layer, which encrypts and decrypts data. All right. Which one is a value used at layer 2? All right, I'll quit at 25. All right, that's the MAC address. Good, popular answer. All right, and a handshake. Which one of these guys has a handshake? There you go, yeah. I'll quit at 25. All right, the only thing that has this handshake is TCP with the SYN-ACK. And this reminds me, you may not have all heard this. So a man goes into a bar, she's a pretty girl, and he says SYN, but she says reset. Anyway, so anyway, Dan Kaminsky about a year ago started on Twitter Proto-Lol, and people had jokes like that by the thousands flying around. Anyway, the guy was named Mango. What's that? What was it? He says she's a pretty girl, and he says SYN, and she says reset. There's a ton of these. Like, I would tell a UDP joke, but you might not get it. So anyway, there was just a ton of these. It became a big meme for a few days or so. All the security guys were writing jokes like that about these protocols. Anyway, all right, so which one is an unreliable delivery protocol? Yeah, Proto-Lol, yeah. Yeah, if you put a hashtag on Twitter, you might still probably be around. It was about a year ago, and there were hundreds of them. Protolol.com. Oh, there's now a .com? Oh, great. Okay. All right. Anyway, UDP is, of course, the unreliable, which doesn't, of course, mean it fails a lot. It just means it does not have a receipt, and you don't really know if it got there. It makes what's called best effort delivery. And under normal conditions, best effort on the internet is more than 99% effective, but sometimes it's not. Yeah.
So Skype uses this?
No, Skype uses TCP, and it's actually encrypted. But you could use UDP it would, for like video conferencing and stuff, but in practice, almost everything is TCP. Even like Netflix, which in practice, almost everybody using TCP, which is kind of expensive for the internet, but it's better for the end user, that every person can like pause and replay their movie and stuff. So if you have one movie and 1 million viewers, you make 1 million separate streams. That provides them the best quality of service, and that turns out to be the one that won in the marketplace. Whereas you would think the technical savings of just making one UDP stream with a multicast would be better, but customers are willing to pay the cost to get the better service they get with an individual TCP stream to each person. And we're just willing to pay for more routers and switches and cables to make that happen. All right, so the TCP IP stack is a more realistic way to describe this, where you take the bottom two layers, physical and these two, data link layer, and you just call it the network interface layer because your NIC handles both of those, the NIC and the cable. Then the internet layer and the transport layer are layers 3 and 4 in the OSI model, and everything above that, you just call it the application layer. And this is more or less the way it really is. You buy a network card that's like wireless, there is no cable, so from the viewpoint of the end user, you only bought one device, and you might as well call this one layer. Then you have your IP for your routers, and you have the transport layer up here with port numbers for your packet filters like your firewall and stuff, and everything above that is just your browser. So this kind of matches how it's actually done in practice better than the OSI model that makes distinctions that really are not obvious when you look at the different pieces of hardware you're purchasing. So IP has an IP header. You definitely should know this. The IP header is the, by the way, IP is also an unreliable delivery like UDP. IP just makes a best effort to deliver things, and it does not have a receipt or detect errors. This is intentional, so it runs fast. If you want reliable delivery, you add TCP on top of it, and TCP will add the handshake and acknowledgments and cost you a lot of time, but make it reliable. And if you want it to be fast, use UDP and accept a unverifiable level of reliability. But anyway, you got the version, which is only 4 or 6. You've got the link to the packet here. You've got fragment offset in IP version 4. You can have data come in with a large segment size, like in principle for something like Token Ring, which had 10 kilobyte frames. So a frame could come in from that. Then you want to cut it into like 5 Ethernet frames, and you do it all at the IP layer, layer 3, so the sender doesn't know it happened, the receiver didn't know it happened. This turned out to be a terrible idea, but you could have a fragment offset and fragment this thing at the layer 3 and reassemble it at layer 3. And this had very little value in actually delivering any real data because there is no actual diversity in frame size that matters. The main thing it does is make it much easier for attackers to sneak attacks through because they can fragment things with frag router, and then they can sneak attacks through because you make it so it only moves like 8 bytes of data per packet, and so the firewall or IDS can't really put together anything enough to decide if it's evil. So this was removed in IP version 6. In IP version 6, you never fragment things at layer 3. All you can do is if you somehow have a large frame size, and then you're going to a small frame size network, you send a message back saying, dude, or in ICMP version 6 saying, your packet was discarded because incompatible frame size, send it with smaller frames from the source. That's the IP version 6 solution to this, instead of having things in the middle, chopping up your data into small chunks, and you don't even know that happened, which turned out to be a pretty bad idea. Anyway, TTL is what prevents the internet from being contaminated because routers tend to have routing loops, especially the early routers that use this thing called RIP, which is not that common anymore. RIP is an inefficient way of exchanging data between routers, and it tends to lead to mistakes, so routers will actually send packets around in a loop going nowhere. And they would clog up the internet, except every time they pass through a router, the TTL goes down. This name is kind of stupid because it has nothing to do with time. Theoretically, it will decrease by 1 for every hop and 1 for every second it waits in the queue, but there is no router queue anywhere where anything would wait 1 second. That's insane. You can go around the Earth in 300 milliseconds, so nobody even bothers to implement that in the code. So it's not nothing to do with time, so they changed it to hop count or something in IP version 6, which is what it really is. But the point is, by the way, it's the simplest way to tell traffic, whether it's Linux or Windows. Windows, I think, traffic always starts with a TTL of 128, and Windows all starts with 64, or else it's the other way. But if you just look at the TTL of a packet, it immediately tells you whether it came from Windows or Linux. And 30 is all you need here. 30 hops will take you around the world. So if you send all your traffic with anything bigger than 30 here, in practice, it will all get there unless something has gone wrong. And so different operating systems just choose a different standard. Anyway, then you got the protocol here, which tells you what's included in the higher level protocol, and a checksum. So those are the main layers in the IP header. That's TTL, like I say. This eliminates packets trapped in routing loops. The early IP version 6 test network, created by GoGo6, which is now extinct, had a lot of routing loops on it. I noticed them it's kind of a fun place to see them. The only other way I know to get them is to set this up with Cisco routers, which we do sometimes in a Cisco class. But they had, so you try to ping something, and it will go back and forth. They went to TTL expired in transit. So if you actually do traceroute, it's going to 10EC and then going to 5 and then back to 10EC and back to 5. This is when you have two routers. This router says Canada's that way. This router says Canada's that way. And they go back and forth. This can happen if they get confused. And this happened a lot in the old days of RIP. In the days of routing interchange protocol, each router would tell the routers around it what it knew, but it would just do it every 30 seconds, whether it needed to do it or not. So you could have a period of 30 seconds when they're wrong before it gets an update. And what's even worse is you could send an update with new information for one router, and when it comes here, this router gets the new information, but then this other router over here sends a copy of old information, which comes in later and overrides the good information. So router gets the truth, and then it gets a lie. Then it gets the truth, and then it gets another lie. So there could be periods of like 10 minutes where routers are sending packets the wrong way. And so this is fairly common. Anyway, not that common anymore. Now the only thing that would really do this is if people are manually putting in routes and they make mistakes, which is more rare, although it can happen too. The TCP header has a lot more hackable stuff, like this window size we were talking about. The window size is there, and like I say, window size can be used both to slow down traffic by choosing the wrong window size. It can also be used for scanning. There's a nmap option to scan for window size. There are quite a few attacks where you send packets to something, and when it replies, you can look at the window size, and that will tell you whether the port is open or not, because remember, the port is open, that window size is changing. And there are tricks where the window size carries information that it shouldn't carry. Anyway, you've got the port numbers, the sequence and acknowledgement number, and someplace, or I guess they call them code bits here, the bits that are like SYN, ACK, FIN, reset, urgent. There's eight bits available, and 7 of them are used as the flags. Anyway, that's the game here, the TCP. And so that's the game. You got port numbers, window size, and there's a common port numbers. You do need to know a dozen common port numbers at your fingertips if you're going to do this stuff. And the sequence and acknowledgement numbers are used to reconstruct packets. Back in the 90s, Kevin Mitnick and the hackers of that generation would hack into people by guessing the sequence numbers. So you can, because there's a fundamental weakness in the system, which is, I think, never written down explicitly. It is very common that due to a variety of errors, switches and routers will send a duplicate copy of a packet. And so every device If it gets a packet it expects, and then another one comes in with the same source port number, destination port number, and sequence number, it is silently discarded. Oh, that must be like an echo. So if you can sneak a packet in ahead of the real user's packet, you can take over their session. And that was the session hijacking Kevin did back in the 90s, where you would get someone to log into a server with FTP, and then you just kick them off and send in your packets instead after they put in their name and password. And now it accepts you as the administrator, and you didn't even steal their password. You just took over their session after they made the connection. A way to prevent this is to use encrypted protocols like HTTPS. That makes it, of course, much more difficult because you don't have the key necessary to forge those encrypted packets, and that prevents you from doing it unless you do something exotic like an HTTPS man-in-the-middle attack to send them the wrong key. But it pretty much means you can't possibly break into a session in progress, unless, for example, you had malware on the administrator's machine that could steal the key. Anyway, so that's the game there. The UDP header is much, much simpler. There's nothing here but a port, length, and checksum. And it doesn't have any acknowledgement, no handshake, no nothing. It just delivers the data, and you don't know whether it got there or not. Because that's the whole point of UDP. You're trying to be fast and efficient, and you don't really care about waiting for acknowledgements. And so it is much faster than TCP, because in TCP you spend long periods of time waiting for an acknowledgement, and you can't do anything about that because you have to wait for the speed of light to get to the destination and back. And if it's in another town or another continent, that's a big pause when you're not sending data, whereas UDP could just be spewing out data constantly, however fast your line goes. All right. So, a few more of these things. Which one encrypts data? Guess I can quit at 25. All right, these better be right. Not that popular. None of those encrypt data. All of those are security risks. They all send plain text data over the protocol as they are. You have to add security to them. Yeah?
What would these answers to?
None of the above.
I know, but which, is there a specific one?
What's that?
None of the above.
None of them. None of these encrypt anything. These are just delivery protocols that just take an address and deliver a packet. There is no thought for security in any of these protocols. If you want security, you've got to add something on top of it, like HTTPS or SSL or SSH. Yeah, yeah. None of these, yeah. Yeah, none of these add any encryption. That's why typically, the IPv6 is not encrypted, although you can have IPsec, which encrypts it at layer 3. Almost nobody does, except the VPN, because it turns out to be very painful to set up. But this is actually a big issue. If you get on the same layer 2 as this other people, you can often just read the data internal. The NSA is our big friend here. The NSA totally did it to Yahoo and Google, and Snowden leaked it. So that was the time after the NSA leaks came out, is the first time people started encrypting their local area network data. Until then, everyone said, well, we only have good guys in the building, so we don't need to worry about that. And now they finally had to admit what everybody knew, which is there are bad guys in the building too. So now they actually encrypt their layer 2 at Google and Yahoo, supposedly. And other companies are beginning to upgrade it. What's that?
Internally? Or?
Yeah, internally. Because the NSA was putting malware on the long-range links between Google centers and Yahoo data centers, and putting a spy there with this kind of router firmware that just leaked. So they were getting all the internal traffic that was not encrypted. This, by the way, is, if you take any cryptography class, and when we teach one here next semester, I will, that the first step in cryptography is check for plain text traffic. Because when people say they're encrypting their traffic, they usually aren't. There's usually some part of it that's not encrypted, and that's the simplest way to hack in. Like most people, 80% of VPNs that people run don't really work because the DNS queries don't go through the VPN. So you can still see what they're doing. And that's why the first step is look to see if the stuff is really encrypted. Usually it's not encrypted, or it's not really all encrypted, and you don't even have to decrypt anything to learn a lot. Anyway, all right. So, which one uses TTL? I guess I'll quit at 30. All right. and that is IP. IP uses TTL because it is moving data large distances, and it might be moving around in circles, not getting anywhere. And TTL is the field that kills off anything that is just hopping too far without getting anywhere. Not TCP, but IP. All right. Which one has 2 versions in current use? All right, I'll quit at 25. All right, and that's IP, has versions 4 and 6. Ethernet actually has 4 versions in current use. I'm not sure how popular they are. There's like Snap. I think they might, yeah, I'm not quite sure about the 802 numbers, but I know you can see them in Wireshark. I think there's one called Snap and something like that. Anyway, but IP has IP4 and IP6, and they're both in current use. I think IP version 6 is now like around 20% of the traffic, and IP version 4 is 80%. All right.
Everyone's popular here.
Yeah.
111.
Yeah, well, yeah. There's no 2 versions of TCP or anything, though. It's the same. All right. Which one is reliable and uses port numbers? I'll quit at 25. All right, and that's TCP, good, good. That's why almost everything is sent this way, because most of the time, why are you sending it? You want to, except that you want to be sure it got there. Where are the Ethernet cables? These are TCP IP layers. Yeah. I'll quit at 25. All right, so that's network interface, which is the lowest layer. Yes, that includes layers 1 and 2. The TCP IP, yeah. Yep, layers 1 and 2 are both in the network interface layer in the TCP IP model. Each model has things that are just annoying, and that's the annoying one here. All right, in the OSI model, the annoying thing is the difference between 5, 6, and 7. Very hard to remember because it doesn't mean much.
You didn't say TCP models.
Yes, I did. Right there. Which TCP IP layer? I did. Should have. Now often,
I didn't read it that way.
now often I'm really wrong, but not this time. Right. So. Right. So how about this one? Where are the IP addresses? He's doing the right thing, though. If anything looks wrong, complain, because I could very well be wrong. All right. I'll quit at 25. All right. And that comment was in fact correct. It's the internet layer. All right. So, but again, not unanimous. That's you call the IP. That's what we call layer 3 in TCP IP. All right. So now there's these ports. Like I say, there's some common ports you should know. There's always a list of them. NGP at 123, HTTPS at 443, and all this jazz. It's probably worth mentioning a couple of.
There's one port that's popular, UPnP, isn't it?
Oh, UPN3. Yeah, UPN. Yeah, Universal Plug and Play. I'm not even sure if it supports it. That's cool because you can send signals and open up ports on the router. Anyway, one thing that's kind of fun is FTP. FTP is really annoying. There's 2 modes of FTP, and one result of it, one of them uses random high-numbered ports. So FTP turns out to be a real problem for firewall administrators. If you want a good time, just Google that. The way FTP typically is you have to allow, I think, anything originating at port 21 to go to any outgoing port. So this is something hackers use. If you put the source port of 21, everything goes through the firewall because FTP is so rude as to not even always stay on the same port. It was designed before firewalls, and it turns out to be a huge problem for firewall administrators. On top of that, it sends your password in plain text anyway, so everyone should just quit using FTP and use secure FTP over SSH, and that will sit on port 22 where it belongs and not jump all over the place and drive you nuts like FTP will. But anyway, so if you want to learn these, there's a flashcard and LinkNet 5, and in case anybody doesn't know, here's the home page for the class, and at the bottom are the links. Here's the links that refer to other things, and here's a flashcard if you want to memorize the port numbers and so on. And it reminds me to play Warriors of the Net after this. Anyway, for people who want to see that. So port types. The first 1024 ports are called well-known ports, which means that's the technical term for them. And the idea was they will be assigned to services that are really important, like HTTP and SMTP, and never move. And on Linux systems anyway, and I think Windows systems too, you have to be the administrator to listen on these ports because they're reserved for system services. All the higher numbered ports you can listen on without being the administrator, and they're supposed to be used for temporary things like games and chat clients and ephemeral ports. An ephemeral port, when I connect to the internet with a browser, at the other end I'm going to port 80 or 443, but at my end I need a port number 2, and that's just a big random number because I'm not a server that anyone's going to connect to. I'm just a client, so I'm only going to use that port for a few minutes and then close my browser and it'll be gone. So those port numbers are meaningless, so they assign the high numbered ports for that. And the original specification in the RFCs says up here above 49,000 should be those ephemeral ports for just the temporary end of a connection that doesn't matter. And the ones in between 2024 and 49,152 should be used for other services like games and chat and all the other things you might want to do, which are not important enough to require the administrator to listen on them, but they should pretty much stay the same for a long time so everybody gets used to what port to connect to. That was the idea. The problem is Microsoft, like it really was. Microsoft, their official policy until 2002 was that security was a waste of time, and they also felt like standards are pretty much a waste of time. Who cares what the standards are? We'll do whatever the hell we want because we have 99% of the desk. We are the standard. So they would write like Internet Explorer that totally does not obey the rules, and everybody says you're going to write your websites the way Microsoft tells you to, or no one's going to see them because everyone's using IE. And they had this attitude for a long time. So up through Windows XP, Microsoft just used all the ports from here to here as ephemeral ports. 1100 was an ephemeral port in your browser, then 1101, 1102. So Microsoft single-handedly destroyed the difference between these two categories. And in practice, there's no difference. Now, since Vista went up, Microsoft actually obeys the rules, and you can see that the Mac does. If I go to a command line and I do netstat minus pant, no, I guess not on this one, netstat minus an pipe more we'll do on this one. All right, so here is me connecting to some web server on 443, and my local port is 61,354. So you see my Mac obeyed the rules. It chose a big number, like above 50,000 for this temporary ephemeral port. These are all the connections of my browser opening some web page. And Mac obeys it, and so does Microsoft now. But in the early days, Microsoft, XP and early, they would just have port 1100 here, 1101, 1102, and stuff like that, which is abuse, violation of the protocols, but there is no punishment for that.
What was the second netstat?
What's that?
What was your second netstat?
Just netstat minus AN. That's the one that works on almost every system. Pant works really well on a bunch of Linux, but AN works, which means all connections and numbers. If you don't use the N, it will not show you like 443, it'll show you HTTPS or something stupid like that. And I want to see numbers. I don't want it trying to, the problem is weird ports, it'll show weird letters, so I don't know what they are, so I'd rather just see the numbers. Anyway, so good. Anyway, let's go back to this, ephemeral ports. So the one thing worth mentioning here, I think is the last slide for some more eye clickers. This is something you have to get used to. This is called encapsulation. So if you start at the top, you're in an application and you do something like write an email, this gets passed down through the presentation, which might add a header to the packet full of something here. Now these headers typically don't really exist, the top three of these. Like I said, the top three layers are kind of merged into one thing. So you have your email, you pass through some transformations, then you segment it, like we were talking about. You cut it up into chunks the right size, like 1,500 bytes typically, and now you add a transport header which contains your TCP port and some other numbers. Then you go down to IP, you take the entire TCP segment and you put it inside an IP packet. And you put another header on it which now has an IP address and a TTL and stuff like that. And then you take the whole IP packet and put it in a layer 2 segment, a layer 2 frame. Then a frame, now you add a MAC address and the layer 2 information here, and then you send it off on the wire. And as we talked about it, actually the wire adds other things which you typically will not see in Wireshark, like start bits and stop bits, but they are in fact added by layer 1. Yeah?
So, but it's not that entire TCP segment that gets put into IP, it's each chunk of the
Yeah,
each
each-
TCP segment.
That's right. So if you have like a megabyte file, it's broken up into little chunks here, maybe 100 or 1,000 chunks, and each chunk individually goes into a separate IP packet. So each little chunk will have an IP, the next little chunk will have an IP, and that's why you have sequence numbers here, to record what sequence number you have. So that's right. It's broken up into chunks, and each chunk, then that chunk gets one here and one here. So this is the thing that it used to, and so what happens is, the stuff the user sees is triply encapsulated with 3 layers of addressing at layers 4, 3, and 2. Then it's sent down your local area network at layer 2 to say the router. The router strips off the layer 2 segment. Layer 2 actually goes to the IP, takes the IP address to determine where it goes in the routing cable, and then it re-encapsulates it with a different MAC address to move on the different local area network to get up to your ISP. Every time something goes through routing, this part is discarded and replaced by the appropriate layer 2 segment for the next bit. So it's sort of like a fish swimming. If you start at layer 7 at the sending end, let me turn on the lights for a minute so you can see this on the blackboard. This is at the heart of Cisco. You take Cisco classes, there's a whole lesson just to get this. You have the sender, and you're up here at layer 7. So you go down through all layers down to layer 1. Then the data is sent down a cable to, say, the switch. And the switch decapsulates it from layer 1 and takes it up to layer 2 to find the MAC address. And it does not decapsulate it any further. All the switch cares about is the MAC address. Now it knows where to send it. So it sends it off to, the, say, the router. Using that layer 2, now the router lifts it up from layer 1 to layer 2 and layer 3. It throws away the start and stop bits from layer 1. It throws away the MAC address. It finds the IP address, compares it to its routing table, and decides where to send it. It might have various wires going different directions. So it decides to send it out this wire, and in order to send it, it has to re-encapsulate it, going back down to layer 2 and layer 1. So it has to add a new MAC address appropriate for this interface, not that one. And a new layer 1 data segment is created, which sends down this other wire to go elsewhere. So you go start at layer 7, you go down, you lift up to layer 2 on your LAN, up to layer 3 on the WAN to get where you're going. And when you finally get to the other end, then at the destination, you go all the way back up to layer 7 again. Yeah?
Can you explain the switch part again?
Yeah, the
I
switch.
don't really get how,
Yeah.
It's just looking for the MAC address, but when you send out the packet, you're not sending it to a particular MAC address. you're
You
sending it
are.
to-
You couldn't see, every single packet has to have a destination MAC address. At layer 2, you must have a MAC address because you're an Ethernet network, and no data can be sent without a destination MAC address. Now you might use a broadcast MAC address like OS, but you have to have one. So even though you put like the IP address of Google here, it has to be sent to the Ethernet address of your router. And so your switches will look at that to move it down the right physical wire to get to the router. And then the router will look at the IP address to figure out who you're talking to on Google, and they'll go to the internet and pass through a chain of maybe 10 or 20 routers to get to Google, each of which will just look at the layer 3 address and no higher. And then when it gets to the final destination, they'll get lifted all the way up.
So when I send something to my router, I'm not using the router's IP address. I'm using
You have a default gateway configured.
right.
So if you use, your computer figures out if it's not a local address, it automatically sends it to the default gateway IP address, and it uses ARP to find the default gateway's MAC address and puts it on the packet. And this is why ARP poisoning works. This is a terrible plan, but this is how the internet is, this is how networks are built. You know you want to go to Google, you know where the router's address is, but you don't know the address you need, which is the router's MAC address. It would probably be a lot safer if everybody typed the router's MAC address in as the default gateway, but instead they type in the router's IP address, and they ask the network with ARP where it is, and that is unencrypted, unauthenticated traffic, so anybody can lie at layer 2, which is one of the many layer 2 attacks that there's really no defense against.
So you send out a broadcast or
Yes.
query saying, where's my router? in the router?
Exactly.
Okay.
And when you get an answer, you believe it, and it doesn't have a password or anything, so anybody can lie, and your computer will just be fooled. It's one of the many really weak spots, and it hasn't been fixed because everyone says, well, that's layer 2, and we shouldn't bother to secure it, we'll just lock the door and keep the bad people out of the room, which is a pretty simple-minded security measure.
Something, but then it caches that are,
Yeah.
so.
For like 2 or 3 minutes, it caches it. So if you keep sending a chain of like bad ARPs every few seconds, it'll live in everybody's cache.
Can you manually set the ARP TTL to a fairly large period of time so that your ARP cache is maintained for your router? Let's say,
I'm sure you can in Linux. I'm not sure about Windows. But yeah, that's an issue. There were simple, Iron Geek wrote a tool called Decaffeinate ID that will warn you when your ARP when your ARP address for the router changes. And most intrusion detection systems will tell you too. And by the way, ARP attacks are incredibly obvious. There's like hundreds of packets coming from one guy. So if you bother to write any kind of detection system, it's actually pretty easy to spot an ARP attack in progress, but it's not by default in any OS. It's one of the many weak spots. Anyway, that's why, to understand it, you really have to understand this way packets are moved.
So attacking an internal network, if you're a guest of someone's network, would be to clone their MAC address of their primary router?
You don't need to.
If I did that, what could I accomplish by cloning it and have my own router? I'm in their network, but I have a different IP. I got an IP from their main router.
Yeah. If you clone a MAC address, you can actually, I tried it in practice. Now, in theory, they will tell you you'll get some kind of conflict. It will warn you. In practice, on real networks, I've done it, you get half the packets.
Half?
It guesses. Yeah. I tried it in the lab. In fact, what happens if you clone the MAC address is the DHCP server will give you the same IP address as the other guy, and you'll get half the packets at random. That's what I find in practice doing it.
Not if you're after the main router. I thought, I'm like, if your main router could be 172,
No,
and
let's draw it up here. So you've got.
So you have one router that's your gateway that's getting a DHCP WAN address.
Yes, let's do that. You have a router up here.
Yep, getting a WAN
and this is like 192, 168, 1.1. And then you connect down here and you're 192, 168, 1.101, for example.
Right.
Okay, now if I'm the attacker, I have to be on this network to do ARP poisoning. So I'd add here. Now I'm going to have, this is going to have a MAC address like AA, let's make it all A's. Okay, if I change my MAC address to be the same MAC address, then there'd be a conflict, but as far as I know, most networks do not have anything that will detect that conflict. So I will enter in the Ethernet switch part of this as that address, and I'll get some of the traffic. In practice, you get about half of it. If I clone this MAC address, I will get a DHCP address, which will be the identical IP address. And Windows XP would detect that, and Windows Vista does not detect that.
Or 10.
And I'm not sure about Windows 10. It might detect it again. What you're supposed to do, see, in Windows XP, when you did DHCP and got an address, it would then do what's called a gratuitous ARP to see, is somebody already using this address? And if they are, I'll pop up an error message and not let you have it. And I think in Windows 10 they put that back. So if you tried to clone it this way, it wouldn't work. But if you clone a MAC address, I don't think anything detects it, and you do get some of the packets. The switch is sort of confused, and it sends some packets to one and some packets to the other.
Couldn't you finish the rest by running Wireshark to that main router to get the rest of the traffic by looking up the main
No,
router?
because modern networks are switched. So if I run Wireshark down here, I will not get traffic between these two devices.
Okay.
If it was a hub, it would, or wireless. So you have to run Wireshark on this device, and that's what that NSA software.
I can't point the Wireshark to that device and
No.
finish the rest. Okay.
Yeah, but what the NSA's been doing, which was just leaked out, is they would just put malware in here to see all the network traffic inside the router. That totally works. Yeah. Question out there?
Yes. Couldn't that be circumvented by port-specific MAC address filtering?
Yes.
Okay.
That is the Cisco solution. That's 8021X.
Yeah.
You configure only one MAC address to connect to each port. Exactly. And that's one of the many reasons to do it. Then only trusted devices can get in, and they have to plug in the right port.
Yeah.
But the penalty is when you change computers and NICs, you have to keep updating that table.
What about turning on the DMZ function and you become the DMZ? Does that help any?
It could, in the sense that it's effectively a VLAN. So if these people were on different VLANs, like if you go to Starbucks, everybody's on their own separate VLAN. So you can't ARP poison the other people through the Starbucks network, but you can do it directly point to point through the unencrypted wireless network. If that Starbucks can't do anything about that. Anyway, these are good questions. Let me just do a couple more of these eye clickers, and then I just want to talk about some administrator stuff here. So I think I got another set of these questions.
I'm trying to make it hackable.
Yeah.
Possible.
Well, these are good questions. Oh yeah. All right. So, where's port 80? 80. Right.
Unless you're asleep.
Yeah. If you only know one port, I hope this is it. All right. So, I'll quit at 25. Is it none of the above? I haven't looked at the answers. No, it's C. All right. Good. But all right. All right. You guys have to leave. Anyway, so all right. So port 80 is HTTP, the most common port. That's what you do for normal web surfing. Anyway, if you didn't get this right, you better do those flashcards because that's not right. You should at least know this one. All right. So which one uses 23? We're at 25.
I'm not sure. That was disabled.
So, because it was disabled, you're able to activate it.
Okay. I think there's some back.
All right, and that is Telnet. And this, oh no, it's SMTP. Pardon me, not Telnet. Telnet's 23. 25 is SMTP email.
Wait, I said 23.
Oh, 23. All right. Well, good. Well, thank you. All right. So the question was 23, and 23 is Telnet. Good. This is good if you people are smarter than me. All right, so good. So this 23 is Telnet. 25 is SMTP.
Yes.
All right. Okay. So where's 443?
Oh.
Another important one.
Yeah. Yeah, it's not on. Technically, it is on. Yeah. One of them's systematic.
Yeah.
It'd be too easy if you forgot it.
I might get punched. Let's see, I'm going to quit at 25, and then we will have a discussion. So, all right, that is SSL.
It's not HTTPS.
HTTPS is HTTP over SSL. So SSL runs on 443. Technically, it's now all TLS. All versions of SSL are now deprecated, but SSL is the secure sockets layer over which HTTP runs.
There's SSL version 2, right?
2 and 3. And now both of them are considered unsafe, and so everything should be TLS now, which is the successor. Yeah, 1.2 is the latest, and most people are using 1.1 or 1.2 now. All right.
SSL is a protocol, not a standard?
Yes, I think so, but I'm not really sure what the difference is. I don't really know the difference.
So
I think it is approved by the IEEE with official RFCs and stuff, so it's a protocol.
Yeah, okay. I meant like it has a particular port that it goes to, not like SSL.
Yeah. I think it does have a standard port assigned to it. Also goes over the same, FTP typically goes over SSH.
Yeah, but I'm just like, I don't know, if I like encrypted something else, but it's just like.
You can move anything to a non-standard port, and people often do for security through obscurity, but they do have an official home where they're expected to be. But you can always move anything to any port.
So they use ephemeral ports.
Wait, we can move anything
Oh,
to any port at any time.
You can move anything to any port, but then what will happen is your clients will have to know to go to that port. If they just like go to their browser and type in google.com, it's going to go to 80.
Right, but we
you-
need to change dedicated ports into undedicated?
You
Like if,
can.
for example, we wanted to put HTTPS on port 14,000.
You totally could. And then nobody could connect unless they knew to type in https google.com:14,000.
Could that also be converted into attacks? People trying to access your network remotely?
The sense in which it's used for an attack that I know is that many people, there are standard ports people use for temporary purposes, like you'll find a website at 80 and their test website at 8080 or 88. So if you go there, you'll often find half-finished versions of things which might be hackable. That's one trick. But moving things to non-standard ports is a fairly common, simple security measure to just defeat simple scanners. However, most of them, if you run Nmap, it'll find them because it still has a banner and stuff. But if you do run Nmap without any parameters, it only scans the 1,000 most common ports. So if you move something to an unexpected port, you will stop some attackers who won't notice it. Anyway, so if you want to do more, I highly recommend this Wireshark 101 book. I did this book and it's very good. This is Laura Chappelle, and you can also, there's a whole bunch of Laura Chappelle videos, and this one here called Network Forensics is the one I saw an hour long that covers almost everything in that book. and you really learn a lot. And this book has a bunch of excellent hands-on projects. You download these PCAPs and see things, and she helps you find out network slowdown reasons and all sorts of good stuff. Yeah.
You took a course, you got a certificate.
I took the course and I got the cert.
Were you using these?
Yeah, I read this book and watched that video, and I passed this test, and now I'm a certified Wireshark analyst, which I don't think will get you a job, but it is pretty good information to know.
Right.
And
Look
so,
good on the resume.
and you can just watch it for free on the internet if you want, or you can get a copy of that book, which is very good. This book is very accurate. She has a ton of projects. I did them all. They really work, and it's full of all sorts of cute little subtleties about ARP and DHCP and good stuff that I wouldn't learn otherwise. So that's one area to go. So
I have
yeah,
a question for you.
yeah.
So what about the router?
Yeah.
Can I do a people injection?
A what injection?
No, Microsoft default address when you don't get a DHCP.
169, yes.
169. So I can do it. Would that help me get anything?
You might possibly be able to put things up on the 160. You can use the 169 address. So you might be able
Inject it into the
to.
main router. Can I inject it into the main router?
There may be, I've never heard of anything explaining that, but maybe there's a way to use it. All right, let me stop the recording, and then I'm going to play, do a little bit of administration here, and then Warriors of the Net. So let me just get rid of this and say what I've got, which is net 2. That'll do. All right. Yeah.